Now we're going to calculate the field of a line charge. So we have another distribution here. And so we have an XYZ axis. And then in red, I'm showing here this infinite line charge along the z-axis. And it has a line charge density in coulombs per meter, and it's designated rho L. And the goal of this section is we want to determine the electric field at some point around this line charge. And so the first part is you want to determine what components of the electric field are present, and then we're going to use rectangular coordinates for this system. So as we vary phi around the line charge, does E change? So if we go around here, go around it, no, pretty much at every point the electric field is the same. And so this is a no. It's basically constant as we go around. And you could think of this as we divide this into some infinitesimal length dz. And so as we vary it around, we could use Coulomb's law. You could say at every point, pretty much the force is going to be the same. And then we do the same thing with z. And z, it doesn't change because if we pick a point here, because it's infinite, the same amount of charge will be above it as it will be below it. So that's a no. And then if we move from here to here to here to here, we know from Coulomb's law that the charge will, the force will become weaker. So that does change. So this is a yes. So this is yes. So it is a function of rho only. So the electric field only has an a rho component. And then, so how do we determine the electric field now? And so I've redrawn the coordinate system, and now we have a field point out here, 0, y, 0. And so this is the vector, and I'm going to draw right like this. Maybe we'll do a different color. So we're going to have a vector going out here, and we'll call this r, and then a vector going out to this point here, and we'll call this r prime. And they use this notation throughout the book, where r prime is always the vector to the charge, and then r is the vector from the to the field point, and then capital R is what we use in the equations, is going to be this vector here. And so to determine capital R, we just subtract the r, which is this guy, from r prime. So just remember this one, because this one's important, that the r prime is always a vector to the charge. And then we go back to our generic formula that we've already stated for the electric field. It's q over 4 pi epsilon 0 r squared, and then this would be the charge to the field point, and then the vector from the charge to the field point. And so how we solve this problem is we just divide this charge, this infinite line of charge, into an infinite number of little differential dz elements. I could say dz, and you'd have an infinite number of them. And then you just integrate over from negative infinity to a positive infinity. So the charge q here is dq is equal to the line charge. Remember, that's in coulombs per meter times the differential z, which is in meters. So that's just going to give us coulombs. And so we pretty much have everything here to solve the problem at this point. Let's go back to black here. And so we have a dE, and then we're going to put in our Q, which is going to be equal to rho L dz, and then 4 pi epsilon 0. Now what is R? R and this point here is going to be rho. We could just call this distance rho, and then it's pointing in the a rho direction. So rho, a rho. And r prime, well, that one's in the z direction, so this is going to be z, a z. Okay, and that means capital R is going to be r minus r prime minus z, a z. And then the magnitude of r prime is going to be the square root of rho squared plus z squared. And so now we have everything to put in there. The little a here, the unit vector, it's just going to be rho a rho minus z a z divided by its magnitude, which is the square root of rho squared plus z squared. And then we have the r squared term there, so that's just going to be the square root of rho squared plus z squared squared. So this is r squared, and this term is the a. In my little diagram, I called it 1t. And so we could say that this is rho L dz over 4 pi epsilon 0, and then rho a rho minus z a z divided by rho squared plus z squared to the 3 divided by 2. And now here we use the previous results where we said there was no z component, just a rho component. And so we could just delete this part here and say, you're gone, because there's no z component. And that leaves us finally with rho L dz over 4 pi epsilon 0, and we have rho a rho over the rho squared plus z squared to the 3 divided by 2. And now we can calculate E. Now we said z goes from negative infinity to infinity, and then we put in that same stuff again, rho dz over 4 pi epsilon 0, rho a rho over rho squared plus z squared to the 3 over 2. And we're integrating with respect to z here. So what can we pull out? So this is going to equal to rho L times rho over 4 pi epsilon 0, the integral from negative infinity to infinity of dz, we'll call this an a rho here, over rho squared plus z squared to the 3 divided by 2. And you could look up in a table that the integral from, well, I'll just say, you could look up in a table or do it on your calculator or whatever, or on the computer, that this integral here works out to 2 over rho squared. So you get rho L times rho over 4 pi epsilon 0 times, that integral works out to be 2 over rho squared a rho. And so this row here cancels with one of the rows down there. And this 2 becomes a 2 here. So that leaves you with rho L over 2 pi epsilon 0 rho a rho. So that is the field intensity around a infinite line charge. And the last part of that section talks about what if the line charge is not at the origin. So I've drawn the line at 6, 8, and then it's infinite along the z direction. And then we want to know what E is at any point around it in space, so some p, x, y, z. And so the distance here from the field to the line, r. So what is r? So r is going to be equal to the square root of x minus 6 squared plus y minus, y minus 8 squared. And that's all square root. There we go. Because you could do right here. Yeah, I don't want to do it that way. Okay, and then from our formula, E is equal to rho L over 2 pi epsilon 0 rho a rho. And we're just going to kind of recast this into the rectangle. So this is going to be rho L over 2 pi epsilon 0 r AR. And then we just kind of plug in everything that we know. E is equal to rho L over 2 pi epsilon 0. And then we have our x vector, which is going to be our ax vector, I should say, plus y minus 6 ay over the rho, which is, or r at this point, I should say, is x minus 6 squared plus y minus 8 squared, and then we have to make this a unit vector. So this is just going to be squared because we have our rho and then our unit vector, which is just the magnitude of the vector. And so how did I get the x minus 6? Because we have we made everything into x, y, z. And so this is just going to be the point x minus the 6, what this is now. So we could do 1, 2, 3, 4, 5. This is, if this is the x-axis, this would be 6. And then on the y-axis, this would be 8. And now we're just doing, and so this would be 6 also at this point. 6, and this would be 8 also, because it's going to be 6 and 8 away at every point. And then we just take the field point minus the charge, which was what we did right there. The field point minus the charge, and the charge is at 6 and 8. So we have the field point xy minus the charge. So field point x, field point y minus the charge. Well, I didn't really like how I explained that, so I decided to think about it and redraw it again. And so we have an infinite line charge at 6, x equals 6, y equals 8, and z is infinite. And then we have some point out here. And so I should actually just keep it in the same notation. So we have r prime is the point to the charge, right? So this is going to be r prime. And then r is going to be the point to the field point where we want to determine what the electric field is. So r prime is going to be 6ax, because we're in rectangular coordinates when we're off the axis, plus 8ay plus zaz. We're at some point z here. And then r is going to be xax plus yay. Whoops. Ay plus a zaz. And now we have our new vector, which I drew before, r, and r is equal to r minus r prime, as I've said before. And so that's going to give you x minus 6 ax plus y minus 8 ay plus z minus z az. So our r is going to be equal to x minus 6 ax plus y minus 8 minus 8 ay, and this is going to go to 0 because it's this z minus z. So this is where you get the off-axis r. And I think that's a better explanation than I gave previously.